Hello students. So today's topic is variable frequency control from a current source and CSI control. So this is unit 4 in continuation with the earlier topics. Now VFC from a current source. So when we have we consider the equivalent circuit for an induction motor, and in that case when you replace the voltage source and put a current source Is in place of that, so expressions which you get in the per phase equivalent circuit, they are shown here next. That is for IR dash T and Im square. These are the expressions which you obtain, and you can just check. So when operated from a current source, when we plot the torque speed characteristics, the curves obtained are the ones showed in figure 6.44a or figure 1a, and 1b is for the Is versus the SF curves. So the natural characteristics in the first curve, that is A part, it is shown in dotted lines, and the curves for the various values of Is, that is Is1, Is2 and Is3, they are shown. So operation of motor above the natural line takes place for flux which is higher than the rated value. Similarly, the operation below natural characteristics takes place at lower flux value. So the preferred operation should be the natural characteristics. And relationship between Is and the rotor frequency SF, as you see in the next figure, that is figure B. So the drive should be operated such that this relationship is maintained when the frequency control is implemented. So for a given Is, the operation of motor above natural characteristics takes place for flux higher than rated and below it at lower than rated. This I have already discussed. And drive is operated such that the relationship of the figure B is maintained between the stator current Is and rotor frequency SF when the frequency is changed to control the speed. So similarly, you can just go through these points. That is, when operating at constant flux, operating points are located mostly on the part of speed torque curve, which gives unstable operation at most of the speed. So closed loop control is sort of mandatory in this, and the motor draws a constant current and develops a constant torque at all frequency. So it operates at constant torque mode from 0 to base speed, and at base speed either rated machine voltage is reached or VFVS voltage saturates. Now the next diagram, figure 2a, you see a CSI fed induction motor drive. Here the magnitude of output current is independent of load, but magnitude of output voltage depends on type of load. An inverter behaves as a current source due to the presence of a large inductance LD. You see here VD is the voltage source, IT is the current we get, and LD is the large inductance which is placed, and capacitors C1 to C6, that is C1, 2, 3, 4, 5, 6, 6 we can see here. They are used for commutating the thyristors. The thyristors are fired in sequence with 60-degree interval. Again, there are diodes connected, diodes D1 and D2 to do D6, and they prevent the discharge of capacitor through the load. So inverter frequency is controlled by adjusting the period T through triggering circuit of thyristors. Fundamental component of motor phase current is 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 equal to root 6 ID by pi. So in this, for any given speed, motor torque is controlled by varying the DC current ID. ID can be varied by varying VD. So there are different circuit configurations which can be used in this. That is, they are shown here in figure 3a and b. CSI induction motor drives, you see with AC supply, a fully controlled rectifier can be used, and then it is connected to CSI and the induction motor. And the next is the DC. If DC supply is used, a chopper can be used, and then in the DC link you have the DC link and again the current source inverter and the induction motor. Chopper will give a variable DC voltage Vt which will further varies It. This DC current is converted to AC by using a CSI and it is given to induction motor. So the main advantage of current source inverter control of induction motor is its reliability. So it is more reliable than a VSI controlled motor, and in case of VSI, commutation failure will cause two devices in the same leg, that is the thyristors which are situated in the same leg, that is TR1 and TR4, to conduct. This connects conducting devices directly across the source, and consequently the current through the device suddenly rises to dangerous values. So expensive high-speed semiconductor fuses are required to protect the devices. But in case of CSI control, conduction of two devices in the same leg does not lead to sudden rise of current through them due to the presence of a large inductance LD. So this allows time for commutation to take place and normal operation to get restored in subsequent cycles. Further, less expensive HRC fuses are good enough for protection of thyristors. So also, as you see in figure 2b, the motor current rise and fall are very fast. Such a fast rise and fall of current through the leakage inductance of motor produces large voltage spikes. Therefore, a motor with low leakage inductance is used. Again, you can go through this point. And large value of capacitors required to sufficiently reduce the voltage spikes. Large commutation capacitors have the advantage that cheap converter grade thyristors can be used, but then they reduce the frequency range of the inverter and therefore the speed range of the drive. Further, due to the large values of inductor LD and capacitors, the current source inverter control of induction motor drive is expensive and has more weight and volume. So this, the last point, it is a sort of a disadvantage of CSI control induction motor. Now the next is the closed loop control of CSI drive. So just as we have seen in the case of VSI control, and there are two loops are there, that is the current loop is there which has the current controller, and there is a summer you can see which has ID star and ID. These are added to sent to the summer, and then the current error is sent to the current controller. Then you have the firing circuit, fully controlled rectifier, and inverter, motor. The motor speed is taken as the feedback, and then it is sent to the speed controller loop, which you have which you see, that is inputs are omega m star and omega m. They are fed to the speed controller and a slip regulator, and then there is a flux control is also there. So the description for this is that this consists of inner speed loop and outer speed loop, and in case of ESI, and this drive operates at constant flux up to the base speed, hence it gives a constant torque operation. Terminal voltage is kept constant above base speed, which gives constant power operation. The actual speed omega m is compared with the reference speed omega m, as you see in the downward side of the lower part of the diagram. The speed error is processed through a speed controller, which is normally a pi controller, and a slip regulator. So the slip regulator controls the slip speed, which is ns minus nr. The sum of rotor speed omega m slip speed omega sl gives the synchronous speed. This determines the frequency of the inverter output. Constant flux operation below the base speed is obtained when the slip speed or the rotor frequency and inverter speed Is have the relationship as shown in figure 4. This relationship is maintained by flux control block. Flux control block produces a reference signal ID star based on the value of omega SL star. Now this ID star will adjust the DC link ID through a closed loop to maintain constant flux. Both speed and current controllers use pi controllers to get good steady state accuracy. If the speed of the drive is to be increased, then the required speed is set as reference speed omega m star. Now the speed error is positive and the slip speed ns minus nr is also positive. So the drive accelerates at maximum current in motoring mode. When the motor speed equals the reference speed, the motor continues to rotate at that speed where the motor torque equals the load torque. So if the speed of the drive is to be decreased, then the required speed is set as reference speed omega m dash. Now the speed error and slip speed are negative. Now the drive will decelerate at maximum current in braking mode. When the motor speed equals the reference speed, the motor continues to rotate at that speed where the motor torque equals load torque. Above the base speed, the motor terminal voltage is kept constant to get constant power operation. Now the flux control block and closed loop control of ID becomes ineffective. Hence the current ID may be increased to higher value, which is not appreciable. To control ID, the speed limit of slip regulator must increase proportional to inverter frequency, and this is achieved by adding a signal proportional to frequency with the regulator output. So this is the description of the closed loop speed control of CSI drives. You can just go through this step by step and understand this. So this is all about the CSI inverter and the control. The reference is Fundamentals of Electrical Drives by G.K. Dubey.